So we talked about PN junction in forward bias, where you connect a cell with some resistance, etc. Higher voltage being given to the P side and lower voltage given to the N side. And then we saw that this applied voltage, if you have this PN junction here and you connect a cell here, so that this is at a higher potential, this is at a lower potential, and this applied voltage is VA, that potential barrier is reduced by this VA. And if this applied potential or that reduction in potential barrier is small as compared to the original potential barrier, then the extra majority carriers which can diffuse, that number goes up exponentially, and then we have this equation I equal to I naught e power EV over KT, this is that we applied, and minus 1. This is known as ideal diode equation. Now before proceeding further, let me just give numerical values of this quantity for different values of applied voltage. This I naught is typically this I naught, which is the diffusion current and same as drift current if there is no biasing, that is typically say few microamperes. So let's say 10 microampere. And at room temperature, at T equal to let's say 300 K, this K into T is 0.026 EV. And if you apply say VA is equal to say 0.1 volt, that means E times VA will be 0.1 EV. So similarly for different applied volts, you will have EV same number, but this volts will become electron volts, and EV by KT. So EV by KT, for example in this case EV by KT will be just the 0.1 and then divided by 0.026, and the EV cancels out. So one can evaluate this number once the applied voltage is chosen, and then you can calculate this whole thing taking I naught say 10 microampere or so. And I have some data for you. If I take V here, applied voltage here, and E, this whole thing, let me take this whole thing, I naught e to the power EV by KT and then minus 1. So at 0, this is 0. This is fine. At VA equal to 0, you have e to the power 0 equal to 1. 1 minus 1 is 0. So that is this. Then if you take 0.05 volt, if you apply this much, then it becomes 58 microamperes. If you take 0.1, then it becomes 458. This is 46. This is not 58. This is 46. This is 46 microampere. This is 458 microampere. And if you take 0.2, applied voltage is 0.2. This is 21.9 milliamperes. And if you take 0.3, this number is 1.025 amperes. And if you take this as 0.7, then you have 4.9 into 10 power 6 ampere. So this gives you a kind of feel that you cannot apply large voltages you cannot apply large voltages here. The diode manufacturer will tell how much current it can sustain. If you send more current than that allowed limit, then this whole diode will be destroyed. So this actual voltage that you apply on the junction should be much smaller than this points. For silicon, this 0.7 is that typically, of course it will depend on temperature and many things, but little bit on doping perhaps, but typically it is around 0.6, 0.7, and if you apply that much, you have huge impossible current, and that is understandable physically. If 0.7 electron volt is that barrier, energy barrier, and if you apply 0.7 volts, what you are doing? You are reducing that barrier to zero. There is no barrier. Then the entire majority carriers this side, entire majority carrier this side can just flow without any barrier. So that will be like a short circuit, So the actual voltage which is applied across the junction is much less than that, and in that limit this equation is usable. Okay. Of course, the diode itself has some resistance to offer. So whatever you apply here may not go on the junction. This depletion layer has a very small number or negligible, we take it 0, no charge carriers, but in any case that that offers a very large resistance. The other regions outside depletion region where you have lot many charge carriers, that offers less resistance, and in ideal case no resistance in fact. So all those things are there. So this is about forward biasing. Okay, there is one more thing that I should tell, that if you have forward biasing, then what happens to the width of the depletion layer? We have derived that equation, that width was some square root of the 2 epsilon, then this volt appearing here, and then divided by E 1 over NA 1 over ND, something of this sort. We had derived that. So when you apply this forward bias, this V decreases. Remember what is this V? This was that potential barrier. So now this V becomes V minus VA. The barrier height is decreased. If this is how the bands are, then this is the barrier height. This is P side, this is N side, and this is EC, and this is EV. And when you apply this forward bias, this EC reduces to some lower value, like that, and hence the barrier is decreased. So this was V, and this is that applied E times, or this is energy, so better to write E times VA, and now this is the barrier. So in place of V, it becomes V minus VA, so it is this. So that means the width of the depletion layer decreases. In forward biasing, the width of the depletion layer decreases, and that has some effect on the current also, because all that thermal generation of electron hole pairs is in the depletion layer. It's other places also, but that is an equilibrium situation. Here, because of the electric field, you have the drift and all those things, so some effect will be there. Now the next thing is reverse bias. What happens if I connect this circuit, but the polarity is opposite, so that higher potential is put here and lower potential is put here? Then what happens? You can very easily guess what will happen. Let me first remove some of this. If you connect it with opposite polarity, so that this side is at a higher potential, this side is at a lower potential, with respect to this side, what you are doing, you are reducing the potential of this side. If I take this as the reference, then by connecting this negative here, you are reducing the potential of this side, and therefore you are increasing the potential energy, or increasing the energy of all those quantum states which are there on this p side. So if you had this picture once again, so in forward bias, this these quantum states, these energies are reduced, but in reverse bias, in this reverse bias, all these energies will go up. So now your EC will be like this. I am writing with reference to this n side, so that's why I am only changing this part like this. So it has shifted up. Okay. So when originally you had these quantum states, and you understand only few at this large energies, there are only few electrons left, all right, because of the Fermi distribution function and density of states. If you are far away from the Fermi energy, this number is very, very small, and only that part was able to diffuse, only small part was able to diffuse. And if you reverse bias, if you increase the barrier, then this diffusion will be further stopped, because now this will not go. Originally when your EC was here, this could have gone, but now that EC is here, this will not go. So the diffusion will decrease, and drastically, because as you go up, the population here, the availability of electrons here falls drastically. So diffusion current will increase, diffusion current will decrease drastically in this reverse bias. Already when there was no bias, VA was 0, then I diffusion equal to I drift, and that is of the order of few microamperes. Okay, so already that diffusion current was small, and then you increase the barrier and it goes exponentially further down. So very quickly this diffusion current will decrease. Nevertheless, the similar the story here, the majority carriers here are holes, these holes like that. As you go away from this point, you have smaller and smaller population, and you have lifted everything up, and anything above this line is not allowed to go here. Your valence band states are here, so anything above this is not allowed to go here, and then you are lifting it up, so that diffusion of holes also decreases naturally. Minority carriers. Now look at the minority carriers, what happens. Where are the minority carriers? In n side, the minority carriers are holes, so these are the minority carriers. And similarly here in p side, the minority carriers are electrons, so here are those electrons. And you can see that minority carriers can easily go. Even in reverse bias, even if this EC has gone up here, no problem for these electrons, they can always go to this n side. And similarly for these holes, even if this EV has gone up, no problem for these holes, they will just go. Hence in reverse bias, the drift is not affected by this increase in barrier. So you will have drift current essentially same. Why essentially? Once again, look at this equation. For reverse bias, this will become V plus VA. Okay, you have increased that barrier, and therefore this width will be slightly increased, and therefore in more region, in a bigger region, slightly bigger region, you have those thermal generation of EH pairs. And if more EH pairs are generated in depletion layer, then the drift current will be slightly more. But that's insignificant, and for all practical purposes, you can take that in reverse bias. This I drift is almost the same, almost doesn't change. But the diffusion current goes down. Already it was this, but it goes down, and therefore this net current, which is now I drift and minus I diffusion, and this will be in opposite direction, in the direction of that drift. So your current is in this direction. So that's the expected direction from the cell also, N to P. This is your direction of I drift. So in this direction, and the magnitude will be smaller than I drift to start with, and then once I diffusion becomes totally negligible, you have applied some voltage, barrier has gone up, and then I diffusion has become almost 0. So it will stabilize at this I drift, which is I0. So on that diagram, IV diagram, on the reverse bias, start with 0, and then it gradually increases to this I naught, and this is known as reverse saturation current. Okay, so it starts from 0, but very quickly it will attain that I naught, and then it will remain I naught for large values of V. No matter how much you increase this barrier, there are some phenomena I will tell, you cannot increase this barrier to very high values before disturbing this. But for reasonable values of V, which could be 2, 3, 4, 5, 6, 8, 10 volts, this side you cannot go even to 1 volt, but this side you can go to easily few volts, it remains at this I naught. Okay, but the scales for this side and this side are very different. If you want to show it on the same plot, because this reverse saturation current, this current here, this current here, this I naught here is of the order of few microamperes. Whereas in forward bias, the currents could be easily in milliamperes, few tens of milliamperes. All right, so this is few tens of milliamperes, 10 milliampere, 20 milliampere, 30 milliampere, like that. So on the same scale, if you show, this line will be very easily hidden in the width of the axis, whatever axis you draw with your pen, pencil or chalk. Okay, so generally what people do, they use different scales here. This scale is in microamperes and this scale is in milliamperes. So you have to read it carefully. So this is how this IV characteristic takes place. Okay, so before talking to what happens if I apply very high reverse bias, I told you that there will be some problems if I apply very high reverse bias. But before going into that, let me show you this forward bias and reverse bias on a PN junction and see how the currents vary qualitatively on the table. So if you go to market and ask for a PN junction diode, this is what you are going to get. Okay, this is one variety. commonly you get this type of p-n junction, and you can see it's a black covering, your all semiconductor is inside that, and at this right end here, this end, you can see a silver band here. I hope you are able to see that silver band. This band here, and that is to tell that this is the n type side of this p-n junction. So this will be your p side where you do not have that silver band, and the other side where you have this silver band, that will be the n side. So that is how I know about it. Now to give a voltage on this, I will be using this battery, and this battery is a 9 volt battery. So this 9 volt I will be connecting to this heater coil. So this is a heater coil, and I will be connecting this to this heater. All this 9 volt I will give on this heater coil. This is known as potential divider. So what I am making is a potential divider. So I connect this end of this is the positive end of the battery to one end of this coil, and then the other end of the battery, this is the negative end, this will essentially go here. So I'll just put this thing here, and I'll connect it later, but I'll connect it here so that this whole 9 volt drops on this. And then I connect I take another wire and connect this, this is the positive end of this potential divider, and I am connecting it here to the diode. So one side I have already given to the diode, and then the other side I am taking it through this galvanometer. This is a galvanometer, and I am connecting this galvanometer to the other side of the diode. So now what is happening? And this end of the galvanometer I will be touching here. So if I connect this battery negative to this point, this is 9 volt here, and then if I touch it here, what is the circuit on the diode? This is now my potential source. I can make it 0.1 volt or 0.2 volt just by sliding. So suppose this is that potential source here, and then from the positive side I am connecting it to the P side of this diode. This is the P side without silver band. So from the positive of this potential I am connecting it to the P side, and then the N side is going to the galvanometer, and then back from the galvanometer back to this lower potential side. So this is a forward bias situation, okay, and the potential that I am giving to this diode, of course the resistances etc. are there, will be just this much, whatever potential is on this. So let's start the experiment. So first I connect this cell here. So now there is a potential drop of 9 volt or whatever is the battery voltage here, and then I can use this much of potential difference to see what happens to this. That you focus on the galvanometer. See, there is a current, okay, see there is a current. As I increase this, you have a current. So this is that forward biasing, and if I do the reverse biasing, let me invert the polarity of this main battery. So I put the positive side here and the negative side here. Now what is happening? This negative side, this is the lower potential, and this will be the higher potential. So the lower potential is connected to P side of this PN junction, and the higher potential side is connected to the N side. So it is in reverse bias. And now I again give potential to this, and you look at this galvanometer. You don't see any current. I am increasing the voltage. See, I am increasing the voltage. I am increasing the voltage. I am increasing the voltage. And there is no current anywhere. Microamperes. You cannot see in this instrument. There is a reverse current, but that is in microamperes, that you cannot see from here. So whatever voltage you apply, you do not have a current in the reverse bias. Whereas in forward bias, you saw that if you apply some sufficient voltage, then you have this current. So the diode offers low resistance in forward bias, and diode offers very high resistance in reverse bias. So now let me talk of what happens if I have very large reverse bias voltage. Large reverse bias voltage also means wide depletion layer, this equation. Okay, if you apply a large reverse bias voltage, you are increasing the barrier, and therefore you are widening the depletion layer. So the electrons or the holes which are drifting because of the electric field, a whole electron pair is generated in this depletion layer, and that electron is, this is the drift, this is the direction of electric field, and therefore the electrons will go in this direction and holes will go in opposite direction. So if this electron is going in this electric field, it is gaining energy. Okay, the electron is going in this electric field, it is accelerating, it's gaining kinetic energy, and therefore, and the depletion region is wide, therefore it has sufficient time also. So it can gain so much of energy in this depletion region because of the effect of this electric field, that it can knock off an electron from the bond, and this electron can produce a new electron hole pair. Okay, so the electron which is drifting in this direction, they can create, these electrons can create, these charge carriers can create new whole electron pairs. And when this electron is accelerated, it can produce yet another whole electron pair here, and this can produce another electron hole pair here. And of course the electrons are all accelerated towards right in this figure, and holes are all accelerated towards left in this figure. So if that happens, it's called avalanche. If that happens, if you apply so much of electric field and the depletion region becomes so much wide that the electrons can create new whole electron pairs, and those can also create new electron hole pairs, etc., then you will have a large current in this reverse bias condition also. Okay, you will have electrons are going this direction, so the current is going in this direction. You will have a large I drift. This is known as breakdown. This is one mechanism. There are other mechanisms also, but the fact is that if you have reached that breakdown, then it can suddenly, the current can suddenly increase many fold. So this will be the complete IV characteristic. This is one branch or one part, forward bias, this is reverse bias, and this is breakdown, and this whole thing makes this IV characteristics. And when you use this as a circuit element, then you have to understand all these things. Okay, so that is for today.